talk a little bit about bond lengths now. Let's talk about hybridization and bond lengths. So we have ourselves sp3 carbons. So these carbons are sp3, both of them are. And the bond length here is 1.54 angstrom. So that's a sigma bond between two carbons. The bond length between the carbons and the hydrogens is 1.09 angstrom. Now, you don't have to memorize this. You could always just look this up if you need to know it. What I want you to understand is the trends. So as the hybridization goes from sp3 to sp2 to sp, the bonds are going to be becoming shorter. And we'll talk about why that would be in a minute. Let me just get the drawings up here for you. So now we have sp2 carbons. And the bond length between the carbon-to-carbon double bond is 1.33 angstrom. And the bond length between the hydrogen and the carbon is 1.08 angstrom. I don't even have these memorized. I'm actually looking off the screen of the piece of paper I have here to remind myself what these lengths are. I know the trend, I just didn't know the number. If I need the number, I just look for it. So don't memorize it. Memorize the trend, and then we're going to explain what happens. sp, the bond length between the carbon-carbon triple bond is 1.20 angstrom. And the carbon-hydrogen bond is 1.06 angstrom. So it appears, and in fact it's true, that as we go from sp2 to sp3, my goodness. Let me fix that. These are sp3. Sorry about that, guys. But correct your notes right here, sp3, not sp2. sp3 carbons to sp2 carbons to sp carbons. As we go from sp3 to sp2 to sp, the bond length between the two carbons gets shorter. The bond length between the two carbons gets shorter. Also, the bond length of the carbon-hydrogen bond gets shorter. So everything's getting shorter as you're becoming less and less hybridized. sp3 is the most hybridized carbon can be. sp2 is the least it can be before going back to being non-hybridized. So it appears that bond length, it doesn't appear that way, it is in fact this way, that bond length is decreasing as you become less hybridized. Why would that be? Well, let's think of it in terms of S percentage. So in the sp3 example, you have 1 part S, 3 parts pi. So that's 25% S character. And 75% P character. 75% P character. Now, what does all that mean? It means that the sp3 orbital has more P-like tendencies than S tendencies. S orbitals are spheres. P orbitals are elongated figure eights, if you will. So the sp3 orbital is going to be quite long, because P orbitals are quite long, and not quite as fat or as wide. Remember, s orbitals are spheres, so they're going to give you some fat character. They're going to make you bigger, more rounded, if you will. So let's look at sp2. sp2 now has 1 part S, 2 part P's. So that's 33.3% S character and 66.7% P character. So now they have more S character and less P character. So sp2 orbitals are going to be shorter because they don't have as much P character to elongate them, and they're going to be a little bit fatter because they have more S character. They have more spherical tendency. They have more of a ball shape. Okay, so they're like an elongated figure eight, if you will, but it's a little bit fat because it has more sphere character than P character. All right, and the same over here. We have a 1 part S, 1 part P. So now we have 50% S and 50% P character. So now the sp orbital in comparison is going to be as short as it can get, because we go back to being unhybridized next after this, and not as short as, basically there's going to be as short as it can get, because the p orbital has the least amount of tendency here. You're only 50% versus 75 and 66. So you're going to lose that elongation, and you're going to gain a lot more girth, if you will. So as you go from sp3 to sp2 to sp, the orbitals themselves are getting shorter and fatter. Okay? So as you become shorter and fatter, atoms have to get closer together to form bonds. That's why the bond lengths are getting lower. Okay? So this carbon and this carbon have to get closer together just to make the bonds, to make the orbitals overlap, than these two carbons do. These carbons can get further away from each other. Okay? And that's how orbital character affects bond length. Now let's take a look at how this affects acidity, bond length and acidity. We know that pKa is a measurement of acidity. How far the equilibrium constant lies to the left or to the right of an equation. pKa of an alkane is right around 50. pKa of an alkene is right around 25 or 30. 5432. pKa of an alkene, 54321. The pKa of an alkene is right around 44. So not much more acidic in comparison. And the pKa of an alkyne is right around 25. So as you go from alkenes, and this is a jump. This is definitely a significant jump here, but not as significant as from here to here. So alkynes are much more acidic. And let's be clear here what we're doing. These are sp3 carbons. These are sp2 carbons. These are sp carbons. So what's happening here? Well, if you examine the anion, this is going to place the anion in an sp3 orbital. sp3 orbitals are quite long. As we learned in the previous slide. Oops. If you make the anion of the sp2, this is going to put the anion in an sp2 orbital, which we know is a little bit shorter. And this is going to put the anion in an sp orbital. Now, we have to think about acidity in terms of anion stability. So the anion, the conjugate base of each of these acids, quote-unquote acids, will dictate the pKa. It'll dictate how far to the right an equilibrium will lie or shift. So now, as we're going from sp3 character to sp character, our bond lengths are getting shorter because our orbitals are getting shorter. So now remember, we're measuring the distance from the nucleus, which is positive, to the tips of the orbitals. So from here to here, the orbital is quite long in comparison to this one. So what's happening is this anion is being held closer and closer to the positive charge, the nucleus, as you become less hybridized. So here, let's say for argument's sake, this electrons are being held one angstrom away. So their maximum distance from the nucleus to the extent of the orbital is 1 angstrom. I don't know what the number is. Let's just say it's 1. This one, these electrons are being held, say, 0.8. So between the nucleus and the extreme far end of the orbital is 0.8 angstroms. I don't know what it is, but let's just say it's 0.8 because it's getting shorter. The orbitals are getting shorter. That's the key. They're getting shorter. So these electrons are held closer to the protons. Remember, to be reactive, you have to be attracted to something else. So these electrons that are here have to be attracted to something that's external to another proton somewhere else. Now here we've gone really short. So up here it's 1, 0.8. Now we're at 0.5, let's say, maybe even 0.4. So these are being held really closely to the nucleus. So now this negative charge here, these electrons are attracted hardcore to these protons that are in the nucleus because they're held closer. So there's less likelihood that they can be attracted away to attack another proton or anything like that. Now they will react. I'm not saying they're not reactive. They certainly are. But the reason why this anion is more stable at equilibrium is because this anion, this pair of electrons, is held closer to the nucleus. The nucleus is what's giving it its stability.